So there is a test coming on Monday of next week. Study materials are up. The plan is for it to be taken during class period, so I'll give 2 hours and 5 minutes for it. I'll let you start a few minutes early or end a few minutes late, but you will have 2 hours and 5 minutes. So I will be available for questions on it. If you know that time's not going to work for you a week from today, let me know soon so we can work something out. Because there's a test in a week, I'm not going to assign a homework for next week. I will post some problems at some point. Yeah, there's not going to be homework due on Monday because there's a test. Plan for today is to go over more with circuits. And a big thing will be learning Kirchhoff's rules for a circuit. Any questions on anything?
We have a quiz today, right?
No,
On Wednesday?
no.
All right.
There's a test coming. Lab is due when your lab is. So if you had lab 2 weeks minus 1 day ago, then it's due tomorrow. It's due when you show up to lab, if you're in my lab. Correct. There will be no homework which is due on Monday of next week, or there will be no homework due next week. Just to, let you focus more on reviewing for the test. It is open book, open note, but if you try to learn all of the material during the test time, things will work out poorly. So if you need to check some equation, that's fine, but you still need to study and know how to tackle problems. All righty. Any questions for the homework that was just due? Okay. Well, I'll post solutions today so you can look over them. Number 4, yeah, unsurprising. Yeah, that one was weird and tricky and kind of cool, but yeah, more out there than the rest. So 4 has 2 plates that are separated. And it had 2 ways of filling that gap partially with a dielectric. For A, had the left half filled. And for B, had the bottom half filled. So you have the equation for a capacitor which is not full of a dielectric. You have one which is entirely full of a dielectric, but half full is a different matter. So the trick which was given in the hint was to look at each of them as if they were 2 capacitors connected either in series or in parallel. So this top case really is the same if you just separate those 2 halves by a little bit. And now you have two capacitors which are in parallel with each other, which each have the same separation as the original capacitor, but half the area. So divide the area in half, figure out what the capacitance would be with dielectric, figure out without, and then use the parallel rule to combine them. The bottom half, instead of being split, oops, that, split like that, into two capacitors which have the same area as the first capacitor, but half the thickness. And one of them is filled with the dielectric. So you can figure out the capacitance of both of them individually and use the series rule to get them together. So that's the approach, and the solution will have the numbers drawn out. Yeah, if you had trouble with 4, don't worry, you're very much not alone. It was meant to be a thinker. You're welcome. I think it would be worthwhile warm up a little bit with some review of something we worked on last week. So we got a 10 ohm and a 5 ohm. And a 30-volt source. So I would recommend first figuring out the current through the circuit, and then using that to find power. So several useful equations for finding power. Current times voltage, or current squared times resistance, or voltage squared over resistance.
For the illustrations, do you care if, or for the homework at least, do you care if we forgot to put that in the homework? I forgot one, which was a problem that was similar to this.
If you didn't put in a picture,
Yeah.
it's okay. If you don't need one.
Okay, and then for the exam, do you prefer that we put a picture in, or?
It's a useful tool. If your equations are all good and I can follow those, you don't need a picture.
Okay.
I wouldn't consider it a requirement. If it's necessary for me to see where you're working through, you can put one in.
Okay, thank you.
But usually I can see where the equations are coming from without a picture, so you should be fine. So it may be tempting to just jump straight into using this equation, using 30 volts and the resistance. And then you have V, you can square it, you've got R, that would give you the power. That does not work because in a series circuit, each resistor doesn't get the full voltage. There's a loss of 30 volts going through both of them. So if there was a 30 volt drop across the 10 ohm resistor, that'd mean there'd be a 0 volt drop across the 5 ohm resistor, and then no current would flow. So that doesn't work. What does work is figuring out the current through them individually. There are other ways of doing it, but this is a pretty reasonable way. So the series rule, resistance is the sum of the resistances of the component resistors in series. So these two resistors together act as if a 15 ohm resistor, act as if they were a single 15 ohm resistor. Then Ohm's law current is equal to voltage divided by the resistance. How much flow is equal to how hard it's being pushed divided by how hard it is to push through. So the current is 2 amps. And they each do get 2 amps. However much current flows through the first one must flow through the second one. So then power for the 10 ohm one using I squared R will be 2 amps squared times 10 ohms would be 40 watts. And for the 5, 2 amps squared times 5 ohms, 20 watts. Any questions on this one?
Okay, so I did voltage squared over resistance immediately, and I got, like, I just added the two resistors together, and then I got 60 watts. So then wouldn't it be like just 40 watts that comes from the 10 ohms and then 20 watts, but like the total? Is that like, do you kind of get what I'm saying? Like the 10 ohm one would give twice as would have twice as much power dissipated as the other one. So could you figure it out that way or no?
You can figure out that way. Did you plug in 15 ohms for your resistance?
Yeah, because that's the like equivalent resistance.
Yeah, okay.
Yeah.
So that would give you your total power dissipated. And the total power dissipated by the circuit using that equation would be 60 watts. And if you knew in series, higher resistors dissipate more power than lower resistors, and it's in proportion to the resistance, you could do the 2-to-1 split and get 40 and 20 that way. It can work.
Okay. Yeah, that sounds good.
It's, I guess, a little more likely to trip you up if the numbers are not as even, but yeah, the reasoning works. Yes. So if you were doing this in a parallel circuit, the total power dissipated by the circuit is distributed differently, and the smaller resistor actually dissipates more power because they have the same voltage across them, and the lower resistor gets more current. Which is kind of neat. And parallel, just jumping to V squared over R would work just fine without needing to divvy it up or use the equivalent resistance of the circuit. Right. Now I just want to show a little more conceptual check-in, and I've got a fat simulation for it. So these two circuits are the two more simple parallel series combinations. The top circuit has a path with two bulbs in parallel. I'm sorry, it has a path with two bulbs in series, and that path is in parallel with a single bulb. And the top circuit has one bulb in series with a combination of two bulbs in parallel. So I'd like to start with the top circuit. And what do you think is going to happen to the brightness of the currently illuminated bulb if that switch is closed and current can flow through the top path? So it's an ideal battery. The bulbs work like ideal resistors. What would happen? Ideal wires. What would happen if we allow current to flow through the top path as well? And we've got a bulb.
And this
So
is
for the top circuit,
yeah.
what's going to happen to the bulb?
All right.
We'll get to the bottom circuit next. So majority answer is decrease. And it doesn't actually make a difference. In a circuit that had resistance in the wires, there would be a slight decrease. That is true, but for an ideal circuit, the voltage across that light bulb is whatever voltage the battery provides. So putting more things in parallel doesn't change the voltage across this bulb. Therefore, it won't change the current through it. So the brightness is unaffected. And this is a big part of why the electrical outlets in a building are usually all in parallel with each other. That way, as long as things are working properly, if you plug in a fan, the lights don't get dimmer. Because the voltage in that plug is unaffected or very nearly unaffected by whatever you plug into the plugs nearby. So yeah, most things that you just plug in are parallel, which is nice. All right, bottom circuit. There are two bulbs that are lit in the bottom circuit, and they may or may not behave the same. So let's start by thinking about what's going to happen to the left bulb. Launch the poll. So what will happen to the brightness of the left bulb in the bottom circuit? Right. Most popular answer is decrease. And how about the right bulb in the bottom circuit? What will happen to it? A circuit breaker trips because there's too much current. So if you plug in too many things, the total current flowing can be too big, or if there's a short circuit, you get too much current. So yeah, too many amps, and then a circuit breaker shuts it off, so you don't have so much current flowing through that you break things or start fires. Right, most popular answer, not change. And let's take a peek at what's going to happen. So the left bulb gets brighter and the right bulb gets dimmer. So this is more complicated. A way of looking at why the left bulb gets brighter. So the total resistance in the circuit goes down if we put in another parallel path. If they were each 1 ohm resistors, initially it would have been 2 ohms, now it's 1.5 ohms. So we should be able to get more total current going through because putting things in parallel drops resistance. So if we have more current going through and all of the current goes through the left bulb, then it should glow brighter. It should dissipate more power. However, for the right bulb, it used to be that all of the current in the circuit had to flow through it. Now, only half the total current flows through it and half flows through the lowest bulb. So it actually ends up with less current than it did before. Another way of looking at it is if the brightness of the left bulb increased and the voltage across the left bulb increased and the current through the left bulb increased. Most importantly, the voltage across the left bulb increased, which means there's less voltage across the right bulbs than there was before. So they should be dimmer. Good on these ideas?
So like mathematically, are these light bulbs more like resistors or capacitors?
Resistors.
Okay.
Current flows through them. They dissipate power. They're quite similar to resistors. Their only biggest difference between a light bulb and a resistor is often light bulbs don't quite follow Ohm's law. They might not be exactly linear, but they're resistors. They work like resistors.
So like in resistor terms, what would be the like equivalent like terminology of the light bulb being brighter? Like what does that mean in like these like electrical terms?
So the brightness goes to the power dissipation. So the more power it dissipates, the more energy it gives off, and a light bulb gives off energy as light. They'll also give off some energy as heat, but so the product of the voltage and the current. But because
Okay.
the resistance doesn't change much, if you increase either the voltage across the bulb or the current through it, the other one increases, so you get more brightness.
Okay, thank you.
Sure. Good questions. This can stop. If you want to play around with it, it's a PhET simulation, PhET. Alrighty. So up to this point, only been dealing with ideal batteries. So I would say, a 5-volt battery, and we would just treat it as if the potential across it is 5 volts no matter what. But a realistic battery, it's hard to get large amounts of current off of it, and current moving through it encounters some resistance. So a more realistic model for a battery is our ideal battery in series with a resistor. And that's a pretty good model for what a battery actually does. So if there is a large current draw from a battery, the potential across its terminals actually decreases. So this would be the internal resistance. And it works a lot like any other resistor would. It's hard to have charge flow through a battery very, very quickly.
Sorry, you said when there's a large draw from a battery, what is it that decreases?
The voltage it provides.
Okay, gotcha. Thank you.
So the 1.5 volts that's stamped on a battery is its EMF. Which gets a super curly E, or just writing out EMF to be clear. Which is electromotive force. Which is very, very similar to the voltage of a battery. A lot of times the terms are used interchangeably, but more precisely, if this is our entire battery, the EMF is what you get across this part, neglecting its internal resistance. And the voltage that a battery actually provides is taking into account its internal resistance. So the EMF is the voltage with zero current. And as more and more current is pulled through a battery, the more and more voltage is lost to its internal resistance, but the EMF would be the same. So there's still the same chemistry process that could, in ideal conditions, give you so-and-so volts. But a realistic battery isn't always going to be putting out that full voltage. So to put an equation for it, the voltage across the battery is equal to its super curly E for EMF minus pi R. And you can get enough current so that you get essentially zero voltage across a battery. So one way of doing that would just be making a short circuit. So if you have a battery and you just connect a wire from its positive terminal to its negative terminal, a very, very good conducting wire that has negligible resistance of its own, the resistance in that circuit is going to come from the resistance in the battery. And the two ends of the wire, those two drawn in points here, will be at the same or pretty much the same potential. So the voltage across the battery is zero because the EMF is just enough to cancel out the voltage drop from its internal resistance. As a rule, you want to avoid doing that because it makes the battery get real hot real fast. In well-functioning batteries, the internal resistance is usually pretty low, so you can get a pretty high current, but sometimes it gets higher. If you wanted to do a full circuit, taking into account a battery with internal resistance, you can just count the battery's internal resistance as, say, a resistor which is in series with the other resistors in the battery. So you could, take this, find the effective resistance as if it were in series, and then it's in series with a third resistor and the resistance of the battery itself to get the total resistance. A little practice with this. So just be the equation voltage across battery is equal to its EMF minus IR. So it's 6 volts. There are series circuits and they're all well and good, and you know how to deal with those. There are parallel circuits. And they're all well and good, and you know how to deal with those. And there are more complicated circuits, which are some combination of series and parallel. And you can deal with those. There is something a little worse, a little more complicated. Let's not call it worse just yet. So a circuit like this, we can have our power source. So right now it looks as if there's just 2 parallel branches, each with 2 resistors in series. So the tools that you already have could analyze this just fine. And now it gets weird. So try and split this up into series and parallel. Where's the starting point of, oh yes, this is in parallel with this, and then we can work out from there. Congratulations, you all got it right. There isn't one. The methods that you so far have just don't work. We can't say that it takes the top path or the bottom path like you would for this circuit here, because it might take the top path and part of the bottom path. That's a valid path. That's a valid path. That's a valid path. And it's possible that all of these paths are, things that current flows through, or electrons might take those paths backwards. So yes, the green path is parallel with the red path, but the blue path just throws everything off. So a new approach is needed. So that's just there to motivate Kirchhoff's rules. If we want to deal with more complicated circuits, parallel and series isn't always enough. But Kirchhoff rules allows analysis of more intricate circuits, more things going on. So you can figure out what current would be flowing through each circuit element. And we got two. First one, junction rule. So the junction rule, if we've got a meeting of wires, let's focus on this point where they meet. We can label the currents we have in these wires. As I1, I2, and I3. Very, very blandly. If more current flowed in to this junction, the spot where all the wires meet, then flowed out, over time, there would be a buildup of positive charge. You get more and more charge just sitting at that point. And that point where wires meet, really hard to build up charge there, really low capacitance. So we can pretty much say you don't build up charge where you just have a junction of wires. What flows in must flow out. And if you think about it just in terms of pipes, if these were pipes each carrying some water flow and they met here, however many kilograms of water was flowing into the spot where those pipes met up must be however many kilograms of water flow out. Otherwise, you just start getting this super dense thing, blow up your pipes. It just doesn't work. What flows in flows out. To put it mathematically, the currents sum to zero. Or sum of the currents is zero at any junction. If you want to look at this rule with a different sign convention, you can just use current in equals current out. So the first way I drew it, I had all the currents flowing into this point. So they could either be positive or negative. Could also draw it as I know I2 goes in and I1 goes in and I3 goes out. So if you were to look at it that way, instead of having them sum to zero, oops, don't sum to zero, they sum to I3. So the total amount in equals the total amount out. So the substantial difference here was how I define the direction of the one that I thought would be going out. If you define plus always to be going in, then things need to sum up to 0. If you define plus to be the way the current is flowing, then the sum of your inflowing currents must be the same as your outflowing currents. Good on the junction rule. I think it makes intuitive sense. Right. Second one of 2. It is the loop rule. So if we have a complicated circuit or a simple one, if there is some loop, the voltage at that point there must be the same as itself. The potential at any given point is the same as itself by virtue of our very, very first assumptions in mathematics. So if we follow the changes in voltage as something travels through this and then gets it back to where it started from, the sum of the changes as it went along those loops must be 0, because if it starts in the same point, it needs to start and end at the same electrical potential. So for this simple circuit here, whatever it gained from the battery, it must have lost in the resistor. You can apply this rule on circuits which have way more going on. A capacitor and a resistor and another resistor, and another resistor and another battery. So you can have a really weird circuit like this. A lot going on. For any loop that you can draw on the circuit, like this one, or that one. There are others. That one. Any loop you can make around is a valid choice. Along any of them, the sum of the voltage jumps you get going through things must be equal to the sum of the voltage drops that you get. Or put it mathematically, the sum of the potential difference changes must be 0. Let us work with this more than a little bit, but let's start simple with it. So there's a junction that is 5 wires meet. So what would the current in the fifth wire be? Yeah, 1 amp out. It's not so hard to see. I want to show you both of the formalisms just so you can, I guess, use whichever one you like and see how they would be different. So sum of current equals 0. If I just define in to be positive, that means we'd have 2 amps plus 2 amps plus 2 amps minus 5 amps, because 5 amps out is minus 5 amps in, plus the current through the fifth wire equals 0. And the only way to balance that out is for I5 to be minus 1 amp. Looking at it the other way, we have 6 amps going in, we need 6 amps going out. So if we already have 5 amps going out, we just need 1 more amp.
Excuse me, Professor, I have a question. In what situation amp would be negative?
So it's just like in what situation is velocity is negative. If you define a certain direction to be positive, moving the other way is negative.
So can we consider current in is positive and current out negative?
If you want, yeah. That works. You can define positive and negative directions for currents. It's like making a coordinate system. For a very complicated circuit, it might be inconvenient to have in always be positive and out always be negative, because you could have something like this. So let's look at I1. If we define I1 to be positive if it's flowing into the junction, then I1 being positive flows out of a different junction. So sometimes you might need to use minus I1 as what's flowing into a junction. The right junction minus I1 flows into it if we define I1 as positive going to the left.
Got it, thanks.
So a lot of times it's just picking a direction to be positive and sticking with it, where the choice doesn't matter much, but sticking to it consistently matters a lot. So the sign conventions are trickier for the loop rule, I think, than they are for the junction rule. So to illustrate that, let's get a circuit going. So if there is a circuit like this, and there's a battery, and a resistor, and a resistor, and a battery, and a resistor. This is not a monstrous circuit, but Kirchhoff's rules would be very handy for looking at something like this. And I can just I1, just picking is going to do that from this junction to this junction. If you were to pick your I1, I2, and I3, you could have made different choices. But for currents, it's good to have them start and end at junctions. But if you had I3 go the other way, it would probably end up being negative, and that's not the end of the world. So for your junction rule, you get I1 plus I2 equals I3, because some of the things flowing into this top bit here must be what's flowing out. But let's look at a loop. And let's look at that loop. That is a valid loop. There are other valid loops, but it's good for showing some difficulties that we might get into. So there are 2 resistors and 2 batteries in this loop. But just going V1 plus V2 minus, what's the voltage across the resistor? V equals IR from Ohm's law. So the voltage that we lose would be I1 R1. This doesn't work because we need to pay attention to the direction that we travel along the loop. So starting here, going through that first battery, we go from minus to positive on that battery, from the negative side to the positive side. So we add V1. If current flows through resistor, it loses potential as it flows through. So the way we're going is the same way as current is going. So we need to subtract I1 R1. Then we get to R2, and our loop goes down through through R2, but the current flows up through R2. So having the loop direction opposite the current direction just puts a minus sign in everything. Because if we were going up, we would lose I2, R2. We lose V equals IR going through that resistor. But in the other direction, instead of that being a voltage drop, that would be a voltage bump. And going through a battery backwards, this loop travels from its positive side to its negative side, which means we're going to end at the lower potential. And that gets us back to where we started. Good on that loop.
Does the longer line on the battery symbol there denote which side is positive, which side is
It
negative?
does. Long side is positive.
Okay, gotcha.
Uh, just as a quick exercise, what is the loop equation for the red loop I just drew in? So where you start is of little consequence. I like to start where I started drawing. So for the red loop, V2 is positive because we're going through it negative side to positive side. Then our current direction of I2 is defined to be upwards. So we need to subtract I2, R2. And then our loop travels through R3. And the current direction downwards is the same as the loop direction. So we subtract I3, R3. Cool. The equations are not so hard. I think the rough thing about Kirchhoff's rules is that you usually only bust them out if there's a circuit that is complicated enough to call for them. So they usually are a warning sign of more mathematically involved computations coming your way. So let's dig in. So there is a bridge circuit. So for a bridge circuit, it is a circuit with parallel paths and a bridge between them, which I think serves as the simplest setup of resistors that parallel and series techniques on their own don't work for. So we can got 1 ohm, 2 ohms, 2 ohms, 1 ohm, and the battery is 12 volts. So I'm going to just define current directions. Other choices are certainly possible. So all of these will work out to be positive. So that's nice. So the end goal of this problem is getting some practice with Kirchhoff rules, but finding the current through the battery. So you could define I6, but once you know what I4 and I5 is, that together will make the battery, or I1 and I2. So if you know the current through all 5 of these resistors, you're home free. So we consider this a system with 5 unknowns. So in order to solve it, you're going to need some equations. And it would be good to get at least 5 of them in order to solve this. There's more than one way to go about it. There are a lot of loops, several junctions you can look at. Just to get us going along the same paths. Do the junction rule for those points there. And let's just make that our starting point. Get our junction rule for just those 2 red junctions. So for the left dot, I1's flowing in, 3 and 4 are flowing out. So for your assumption of I2 needing to be half of I1, that rests on the assumption that all 12 volts are gone by the time it reaches the red dots. But the voltage across I1 isn't 12 volts. Because if it were, there'd be no potential left to go as it travels through I4. So it does work out to be trickier than that. The right red dot, I2 and I3 flow in, I5 flows out. So for the loops, there are a lot of legal loops you could do. Could do this loop. Perfectly legal loop. Just so we run the same problem, let's all get the equations out for this loop. For that loop. And for that loop. So be particularly careful with your positive and negatives for the third loop, the green one. So yeah, see if you can get out your 3 loop equations. You could do more than 3, but we've got 5 unknowns, so 5 equations is good. The delta star transformation, the delta star formula is something you can use. I would like you to learn Kirchhoff's rules also, because if you're not just dealing with resistors, it can be harder to use the delta formula, but it is a cool trick. But if like every wire had a resistor and a battery on it, things get rough. But it's a mathematically legitimate trick. For the inner loop, starting at the battery, just have 12 volts. And then we move through our 1 ohm resistor, where our current direction is the same as the direction we're traveling with our loop, downwards and to the left. So we get minus 1 ohm I1. And then we have a voltage drop as we go through this 2 ohm resistor. So minus IR will be minus 2 ohms I4, and that gets us back to the start. For the outer loop, it's pretty similar, starting at the battery with 12 volts, then traveling through this 2 ohm resistor here in the direction of I3. And then this 1 ohm resistor in the direction of I5.
Excuse me, Professor, that would be I2 minus 2I2.
Oh, you're right. I misread that one entirely. That is a 2. Thank you for catching that. It's 2 ohms and it's I2. And for the green loop, we go through I1 in the direction of where the loop and current direction are the same, then through that 1 ohm resistor where I3 is flowing in the direction of our loop travel. And then we flow through the 2 ohm resistor where I3 is opposite the direction of our loop. So minus 1 ohm I1, minus 1 ohm I3, and then we get a sign flip because our loop direction and current direction are opposite. And these are our equations. Solving it, still more work, but I think the most important step is getting this set up. Yeah, the green one is a legal loop. No batteries in it, but the potential as you go through it better end up being zero change. So yeah, it's a different kind of loop, but at that top point there's a certain electrical potential. So if you go around a loop, when you get back there, you better be at the electrical potential you started with. So yeah, loops without batteries, just fine. Later on, if you start looking at circuits, you might have a loop without a resistor in it. Just other circuit elements. That's okay. If none of your loops have the battery in it, you'll likely run into problems. And if you use the junction rule for everything and don't use the loop rule at all, you'll likely run into problems. But if you just do a bunch of loops, it'll probably get you mathematically to the solution. Junctions can't ever get you there on their own, because if you double the current everywhere, the junction rules would still hold true. So in order to get a solution, you usually need at least one loop. But the perk of junctions is they make it real easy to mathematically eliminate one of your variables. All right. So it is just algebra from here on out. I'm going to see if you can, well, let's see if you can work it out. If you want to work on your own, you can. If you want to work in groups, you can. Make sure you get all of the information before you go if you're going to go. So if you want to try team working it, you have that option. Yeah, you can calculator it. Or, you know, Google linear equation solver if you know how to type it into one of them. Yeah. So yeah, work it out. So a good way to go, find a variable that you can eliminate or express in terms of other things, and then just keep doing that until you have fewer and fewer unknowns. How's it coming along?
It's not going great. This is a big system.
It is. It is.
I've just decided to redo all of my I with numerical subscripts as A, B, C, D, E.
That's not a bad choice. Yeah, that's fair. Just so you don't have numbers turning into variables and variables turning into. I1 equals I5. All right. So currents should be in amps, but the numbers seem reasonable. Amps instead of ohms. So resistors you measure in ohms. Let's just show how some of this can be done. And yeah, it's no small amount of algebra. So my approach was first finding a way to eliminate I4 and I5. So I4 is I1 minus I3. And I5 is I2 plus I3. And this green loop gives us a way to isolate I3. Is going to be 2I2 minus I1. So this new value for I3 can get plugged into our equations for I4 and I5. I1 minus 2I2. And then it has to be plus I1 because we distribute that minus sign. And I5 is I2 plus 2I2 minus I1. So I4 is equal to 2I1 minus 2I2. And I5 is equal to 3i2 minus i1. And then these can get plugged into the loop equations for the goldenrod and pink loops. It can be easier to get the voltage on one side and the currents on the other, or not. And just simplifying this up, this gives us 3i1 minus, sorry, our minus signs cancel out to give us minus 1 ohm I1. Oh, I'm sorry, minus 3 ohms I1. Plus 4 ohms I2. Where did I go wrong? Oh, this should be a plus sign. That's my problem. So yes, 3 ohms I1 minus 4 ohms I2. And similarly into the pink one, we can sub in our new equation for I5.
Professor,
Yeah,
shouldn't it be 4 ohms I1 or on the right side, and then you're adding one more ohm I1, so it should be 5?
yep,
It's just because you had the negative sign before.
yeah. Thanks for catching that. Yeah, it's no small amount of algebra.
Yep.
And the problem is one mistake carries. So plugging in for this one, we have 2 ohms I2. And then we need to add in 1 ohm I5, which is 3 ohms I2. Minus 1 ohm I1. Or 1 ohm I1 plus 3 ohms I2. And now it's just 2 equations, 2 unknowns, looking more and more manageable. We can get an expression for just what I1 is on its own. So it would be 12 volts over an ohm minus 3i2. And that can get plugged in. Ohms. Minus 3i2 minus 4 ohms I2 And this is one equation, one unknown. And once you have that one, you can plug the values back into everything else. I believe the calculated answers look good, just in amps instead of ohms. Let's see if we just look at that path. Does it follow the loop laws? So 5.14, 1.7, 5.14. That's, yeah, it looks like it's checking out. Cool. The principles aren't so bad, but yeah, the problems, they get involved. For an easier to work with system, we can get by with less complexity and less going on if we actually throw in another battery. So an example that uses that is here. So there's our top wire, there's our bottom wire. And there are 3 paths. The left path, the middle path, so you can get by with only 3 currents to start off with, which cuts the algebra down by a lot. Because the top junction and the bottom junction are essentially the same, they all are interactions between the same 3 wires. I recommend using 1 junction and 2 loops instead of trying to use 2 junctions and 1 loop, which would be problematic.
Is that 10
Equations would
ohms
end up
there
being
on the
same
left?
equation, so it wouldn't quite work. So try a junction and 2 different loops. Focus on the setup and see how far through you can solve it. Right. You could have done or been in the process of doing entirely correct work, despite making different choices from the choices I'm making. and that's fine. So if you are doing it with different choices, that doesn't mean wrong, as long as you're being consistent to them. Oh, I think it was in the chat, it's just in amps instead of ohms.
Yeah, I got a different answer than what the chat answer said, and I don't know if I'm making a mistake or not. It's just very complicated. It's a lot of things being put together.
It is. Let's work with this one. This one
Yeah.
is cleaner.
More
Uh,
batteries is cleaner.
Yeah, it is odd that 2 batteries lets us actually make an easier example, but it does. So for the loops, there's one. And there's one. And for the junction, there's a junction. I like having my currents be positive, and looking at it, I have a pretty good idea that it's going to be flowing up on the left, up in the middle. That's the way the batteries are pushing it. And due to that, down on the right. If my guess is wrong, I will get a negative current, and that just means it's flowing the opposite direction I put in the arrow. Not a big deal. Sometimes you guess wrong, and that's fine. Or you don't even try and guess right. You just make the arrows go in a way that looks nice to you. But I'm going to go I1. Like that. Unless it's defined as positive in a certain way in the problem, if you defined a direction and it's going opposite, yeah, it is negative. Yeah, absolutely. If a question asks for the magnitude of the current, give it as positive. So for the junction rule, I1 and I2 flow in, I3 flows out. I1 plus I2 equals I3. For my left loop, I have 8 volts minus 10 ohms I1 plus 5 ohms I2 minus 6 volts. And for my right loop, starting at that battery, I'm going forwards through everything. 6 volts minus 5 ohms I2 minus 15 ohms I3. Equals 0. The equations can be simplified a little before even combining them. We get 2 volts is equal to 10 ohms I1 minus 5 ohms I2. And for the left one, everything can just be divided by 3. So 2 volt. Oh, wait, no, the 5 can't. I mean, it can, but just not cleanly. So I'll just keep it as a 6. 6 volts. And now we've got our equations 1, 2, and 3. Algebra tricks as you will. I think turning I3 into I1 plus I2 is a good one. And collecting our terms together, 6 volts equals 15 ohms I1 plus 20 ohms I2. And we can get an expression for just I1 or I2 on its own, where I2 is now let's make it I1. 0.2 volts over ohms minus plus 0.5 I2. And that can get plugged in to there for a solution. Good on our process here.
What were the actual answers?
I guess, all right, I can keep running with it. So plugging that in. So this 15 times 0.2, I want to bust out a calculator. It's going to look ugly. Yeah, it's not too hard, but I don't want to mess up a decimal. I don't think it's going to come out to a nice simple answer. A nice
I
round
got 4
number.
11ths.
Did you get one?
Yeah, I got 4 11ths.
4/11ths?
For I3.
Cool. I'll double check it. And Wednesday give a check-in. 4/11ths. Cool. All right, then we got it. 4/11 amps for the 15. Right. That is good for today. The rules, not so hard. The math takes some grinding to get through. They tend not to be easy problems. On Wednesday, we're going to look to what happens if we have a circuit that has both a resistor and a capacitor in it. So Kirchhoff's laws are useful for analyzing that, but we don't need to make the very, very complicated arrangements of things, but just how would they work together? So we end up like, how would you charge the capacitor or discharge a capacitor? So that's what we're going to look into next time, which is in chapter 26. All right, cool. Anything else for today?
Nope. Thank you, Professor.
All right,
See you Wednesday.
see you Wednesday.
Thank you, Professor.
Thanks.
Professor,
Yeah.
quick question about it.